This is O-Levels, October-November 2023, paper 1-2. Question number 1 says to read the scale in centimeter cube. So it's just about reading the scales in between the lines. We must be able to do that. So this is starting from 20, ends at 30, which is most likely going to make this one as at least 25. It's less than 25, so it's going to be 24. Be careful that these are actually 10 divisions, right? So 10 divided by 10, or you can say a difference of 10 centimeter cube between 10 and 30 and 20 leads to 1 centimeter cube per division. Okay. Question number 2 is a repeated question from past paper. It says that distance time graph is given. So first, starting before starting the question, we understand that the gradient is going to represent the speed as it is going to be change in distance divided by change in time. That distance over time becomes speed. So the gradient is constant. We can say it's a straight line. So then the speed is also constant. This is the conclusion that we've drawn before reading the question. The car is traveling along in a straight line, along a straight road, up a hill. So for example, if this is a hill, the car is at this point, it's moving up the hill and is probably, yes, most likely moving at a constant speed. Okay. But then he says, what could be, which quantity of the car is constant and greater than 0? So if from the graph we have seen that the gradient is constant, which means the speed is constant, that means the acceleration is 0. He's asking us that it should be greater than 0. So the first option gets cancelled out. Moving on to the next is displacement. It should be constant but greater than 0. Since the car is constantly moving ahead, the displacement is not 0. The displacement is forever changing. That is again going to be the wrong answer. Then which quantity for the car, again, the gravitational potential energy should be constant, greater than 0. Now, it's greater than 0, but it's not constant because you're constantly gaining height with reference to the Earth's surface. First, this was the height, then this was the height, and then this was the height. So at every stage, the value of height is increasing. So the value of gravitational potential energy is also increasing. So it's not constant. That's where it fails. So option C is also wrong. By that answer, option D is the correct answer. Plus, we understand that the speed is constant. So whenever I apply half mv squared, the mass is constant, the velocity is constant, I'm going to get the same answer no matter the object was at this place or the object was at this place, wherever it was in its life cycle. Question number 3 says, speed time graphs, speed is being represented and acceleration is being represented by which respective graph? So we have a distance time graph and a speed time graph. What can be deduced from their gradients, for example? So area under the distance time graph has primarily no meaning. It's a wrong question. So option A and B are going to get cancelled out. The gradient distance time graph, yes, that's more likely. And acceleration is again the gradient of a speed time graph. The area under the speed time graph represents the distance moved by the object. So question number 3, the answer is going to be D part. Question number 4, a very straightforward question is asking you about the density. We can verify this from all the units of the answers as well. He wants to ask the density of the stone. So that's going to be density is equal to mass divided by volume. So mass is already given to you, which is 65 grams. What's the volume? So primarily or previously, the initial volume is 30 centimeter cube, and the current volume after pouring the cylinder with the stone and the water, it's 55. So water level rises from 30 to 55. So the volume of the stone actually will be 55 minus 30. You can directly write down 25 as well. So when you solve this, you're going to get as 2.6 grams per centimeter cube, which is going to be option D. Very easy, very straightforward question, and one of the repeated ones. Question number 5 says a submarine has a mass of 1000 kg, sinks at a constant speed of, now always pay attention to this letter, constant speed. It means that the resultant forces or the forces acting on the object have produced a zero resultant, which means that whatever the weight of the object was, whatever the drag experienced by the submarine is while going downwards, and whatever the upthrust or the buoyant force is, they're all balanced. They're all equal to each other. So in this circumstance, we can say that the weight is equal to the upthrust plus the drag of the object while the submarine is moving down. And upthrust is the force provided by water by its displacement. And we understand it, we observed it in real life as well, that if we have a glass of water, for example, we place ice cubes in it and it floats. They don't sink. right? So that force which stops this ice cube from going down is the upthrust. And every object submerged in liquid experiences that force. So apart from this idea, upthrust is not a part of your course, but for the sake of understanding, I'm explaining it. I'm using this word in this question. So always pay attention to this word, constant speed. It means that all the forces are balanced. Forces are not zero. This is not zero. This is not zero. This is not zero. Their resultant, their combined effect is zero. What is the resultant force? So again, I've already discussed this question so much. The question is straightforward. The answer is going to be, or would have been, option A. And I would not have wasted time if I was solving this question. If I read constant speed, resultant force is zero. Question number 6, again from terminal velocity and free fall. He says the object experiences air resistance, so air resistance is present. What happens to the velocity and the acceleration of the object? Now, if you release the object from rest, for example, as it starts falling down, its speed will increase. That's for sure. The speed, for example, initially is 0 meters per second because it is at rest. When it starts falling, its speed increases. So, for example, at this stage, the speed is 37 meters per second. So the speed had to increase. So the velocity increases. Option A and B were not possible. Then you move towards acceleration. What's going to happen to acceleration? Now, acceleration decreases. Why acceleration decreases? At the very beginning, the acceleration is 9.81 meters per second square. At the end of its life, it's going to be acceleration equals to 0 meters per second square when it eventually achieves terminal velocity. What happens at that stage? So the downward weight becomes equal to the drag. At that moment, according to F equals to ma, there is no more resultant left. The weight becomes equal to drag. So the equation is W minus D equals to ma. When both of these values are equal, this side of the left-hand side of the equation becomes 0. So 0 equals to ma. Mass is not 0, so most likely acceleration is equal to 0. So this actually happens gradually. So at the start, it has 9.8 and eventually it gets to 0. It reduces to 0. So acceleration is decreasing, or it decreases throughout the motion. So C will be the answer. Question number 7. You'll have to guess some of these things. It says the stopping distance measured in certain conditions. Okay, fine. Dry road with new tires, old tires, wet road with new tires and old tires. So he says which two results possibly measure on the dry road with old worn out tires. Now, first of all, we are using the same condition for both of the tests. So the results should be very close to each other. This is the first observation, right? So it can't be possible. It's not possible that one of the results is 12 and one of them becomes 40. Or one of them is 12 and one of them becomes 17. Since you're doing the same experiment twice, the results should be very close to each other. But the closest results are going to be 16 and 17. So by that logic, we can understand that option B is the correct answer. But there is a problem. Some students may argue that what if we categorize all of the situations? So first condition, dry road, new tires, the best possible condition. So this is our case W, when everything is fine, when everything is ideal. And on the wet road with old tires, this is your situation Z. Okay, fine. But then how do you make a decision between these two, right? The question still remains. Where do you categorize these situations? Because you haven't done this in real life. So although this helps you out to figure out that this is the condition that still has to be taken decision for, but then again, it doesn't answer the question. So to answer the question, we had to rely on this logic that the experiment is repeated in the same condition. So the results should be very close to each other. Okay, so the answer is going to be option B. Okay, question number 8. It's tricky in terms of its wording. Otherwise, the question is very simple. He says that when 200 grams is hanging, the total length, again, notice that starting from the starting point and ending at the full length of the spring, is 9 centimeters. But in the graph, he's mentioning extension. Okay, the change in length, the change of length when you put on some mass. So let's go ahead with this. He says that now this 200 is replaced with 100. What's the new length? Please be advised, it's length, not extension. So if at 200, the extension is 2 centimeters, we can predict what would have been the true or the original length. You see, if you remove this 200, where would it go? Where would it settle down? Its extension would reduce and it would settle down at somewhere along 7 centimeters of length. Because only when you put in 200 grams, it extends by 2 centimeters and its length increases from 7 centimeters to total 9 centimeters. So there is an extension of 2 centimeters as picked up from the graph as well. Now, if you replace the mass with 100 grams, it means that you're going back. You're going to reduce the stress. So the extension today is only going to be 1 centimeters. There are two ways to look at this. Either you can compare this by reference case, which is that the original length or the unstretched length is 7 centimeter. Adding 1 centimeter to it will give you an answer of 8 centimeters. Or you can go about in the other way, that if the current situation has 9 centimeters, whatever the length is, there is an extension of 2 centimeters built into this 9 centimeters. Today, the extension reduces by 1 centimeter. So now this is going to be L plus 1. So there is a reduction of 1 centimeter. So 9 minus 1 also gives you 8, or 9 less 1 centimeter also gives you 8 centimeters of answer. So B will be the answer. Question number 9 is very straightforward. Circular motion. The resultant force is always in the direction towards the center of that imaginary circle, wherever this object is going to go. Part B has no meaning. Part D has no meaning. Part C has some meaning in development of the centripetal force, or the requirement centripetal force. This is called the tangential velocity, or the component of velocity. This is your centripetal force and the direction of centripetal acceleration. And this is the direction of resultant force as well. Okay. Question number 10. So these are going to be no-brainers. You're going to solve them and select the option that put you towards the center of the circle. No questions asked. Move ahead with the question. Question number 10, he says, which expression equals to impulse? Now, this is the first time he's going to answer the questions regarding momentum. So we understand that the equation for force is equal to change of momentum divided by change in time. When you take this to the other side, this becomes F into delta T equals to delta P. Now, this side is called the impulse, and this side is called the simply translated in English, a change in momentum, right? So he says what impulse is equal to. Is it equal to change in momentum into divided by time? No, this is equal to force. Is it equal to change in momentum? Most likely, yes. Is it equal to force into distance moved? No, that is work done. Is it force over area? No, that's pressure. So B is the English translation of this proof. Question number 11. This is from work, power, energy. Just a tricky question, but let's try to solve this. He says that there is a constant force F trying to drag this object in the forward direction, let's say, and the mass of the object is 4 kg. The constant friction force backwards is of 1 Newton. When the box has traveled 1 meter, its velocity is 1.5, which means that the box currently is at this location. But wherever we are talking about is this current position, the force is still acting on it, the force of friction is still acting on it, but it has moved a distance of, from the starting point to the ending point, a distance of 1 meters. So one thing is clear, whatever work done was there, whatever energy has been spent, some of the energy had to be spent for friction, because friction is removing energy from the system. The kinetic energy of the box, now this is where the equation, this is where he's helping you, this is where he's giving you the hint, is equal to the work done on the box. What sort of work done? Work done by the force F and some of the energy lost in friction was all done by the force F. So force F has done two things at the same time. Not only is it working against friction, but it's also providing some velocity to the object. You see, the box previously, or let's say the box may have no velocity at the start of the motion, but now it does have some velocity, right? And here we can see it's starting from rest. So previous velocity was 0. Today it has a velocity 1.5, which means that this force F has done two jobs for us. It has done two things for us. So by the law of conservation of energy, we can see that the work done or the energy poured into the system should be equal to the energy extracted from the system. So whoever contributed the energy is our force F. So capital F multiplied by 1 meter of distance, which is F into D, work done, equals to energy used. Where has it been utilized? Where do we see that it was utilized or used up? So I can see it was used up in friction. And again, we have the force of friction. We know the distance, so it would be F into D. So force of friction multiplied by its distance, the energy lost or energy used. Plus one more factor was involved. So this force not only moved it from the position, it also provided it with kinetic energy. And the formula for kinetic energy is half mv squared. So the mass is given to us as 4 kilograms, which is 4, and velocity is 1.5 whole square. When you solve this, this is going to come out as 1 plus this is going to come out as 4.5. Now, when you take this 1 and take this other side to divide this, it doesn't matter. So this comes out as F equals to 5.5 newtons, which is going to be 11D, right? So we understand that some of the energy, some of the work done was done to provide kinetic energy. Some of it was used to do work against the kinetic work against the friction. Okay, all right. Question 12 is very simple, very straightforward. He asks you where it has the maximum gravitational potential energy. So we can see that at this location, we have this location, and then we have this location. So if this was the surface of the Earth, wherever we were, if this was the surface of the Earth, which point has the highest displacement from the surface of the Earth? So in terms of C, this is the height. In terms of B and D, they're both exactly the same. This is the height. Let's call this H1. Let's call this H2. And let's call this H3. Which one has the greatest height? So I can see that when I apply mgh, unless or until I put the largest value in h, I'm not going to get the highest answer. So the greatest potential energy or the maximum potential energy will be at point A, because that is the highest point above the surface of the Earth. Okay? All right. Question number 13. How does an oil-fired power station differ from nuclear power station? You see, primarily, both stations or any power station's primary job is to convert any sort of energy or any source of energy into heat, into thermal energy, so that we can boil water. From boiling water, we provide that boiled steam to steam turbines, and then we start moving, then it moves the prime mover of the AC generator, and then we get electricity. The main difference between all generating stations is how they make heat. Now, nuclear power stations make heat by nuclear fission process, by breaking down the nucleus. Oil-powered stations actually try to burn the fossil fuel. This is where the problem lies. This is where the environmental factors, or you can say the global warming, comes into play, right? So he says, how is it different? The end product is same. The middle product, the boiling water and the steam, is same. The starting point is different for both of them. So again, steam produced is same for both of them. Hot steam used to turbines, same for both of them. Turbines used to, these three steps are exactly the same for both generating stations. The only thing different is in oil farm power station is that gases contribute to the atmosphere and the global greenhouse effect. Question number 14, a very straightforward question. He says that the energy provided to the load is called GPE, gravitational potential, and it is also moving, and the load has some kinetic energy because it is moving. Okay, fine. Which expression is used to get the efficiency of the motor when the load is being lifted at a constant rate? You see, when it is moving at a constant rate, that means that the kinetic energy is not changing anymore, which means that whatever energy you were supplying, it is only converting into gravitational potential as it is being lifted up. It is not converting into kinetic energy as it is moving at a constant speed. It's not converting into, it's not contributing into, it's not spending its energy to give something to kinetic energy, which means that at this exact moment, the output energy is gravitational potential and the input energy is electrical energy. Now let's see which option does that. So first, we need to put the useful output in the numerator and the total input in the denominator. Gravitational energy gained per second. Okay, this looks like a good option. Divided by kinetic energy, no, it should have been total input energy. So the power supplied looks good. Gravitational potential gain per second, this looks good as well. Still fingers crossed. Power supplied, no, it should have been in the numerator, denominator. This is the wrong implementation. So C is completely wrong, A is completely wrong. D says efficiency is power supplied. Again, it should have been in the denominator. Now, what's with this? We are dealing with power, but we're talking about gravitational potential energy. In efficiency, we understand that it should be joules divided by joules, or it could be watts divided by watts. The unit should be the same for the efficiency formula to work. But how can we say that this option is right? Although this is the right answer, but how can we say that? Okay. Now, the answer lies in this idea that if you look closely, the unit of power is watts. Okay, fine. But what's the unit of the numerator? This is energy. And when he says gained per second, it means that energy is being divided by time. Now, when I go to power formula, or the formula for power, that is work done divided by time. What's the unit of work done? The unit of work done is joules being divided by time, which is seconds. What's the unit of energy? That is also joules divided by time, which is seconds. So the unit is same, which means that the numerator quantity is also in watts. The denominator is also in watts. So watts divided by watts, this option is good enough. Okay. Question number 15, one underlying mistake that you're going to do and get the answer as option A. I will show you what's the problem. It says how long the motor can be switched on for. So 3000 energy, 2 watts is the power. So power is equal to work done divided by time. I generally recommend my students that don't remember this by work done, although always remember this by energy divided by time. You see, both have the same units. If the units are same, then they can be interchanged in the equation. So I'm spending 3000 joules of energy and the power output is 2 watts divided by T. So I take T over there. So T is equal to 3000 divided by 2, which becomes 1500. Now students become very hasty and mark option A as the answer and move on. This is the wrong answer, because in this equation, time is actually found in seconds. If the time is in seconds, you can see that all options are representing minutes, then you have to convert this into minutes. So this is going to be divided by 60 and the answer is going to become 25 minutes, which is option D. Be careful. Question number 16. We have, man finds it difficult to hammer a wooden block. How can he make it go more easily? Make it pointed, yes, to increase pressure. We have force over area. We can't increase the force we are providing from the hammer. We can reduce the area of the nail, make it more pointy so that the pressure increases. So this looks like a good option. Make the top of the post pointed. No, that will not help. Use a longer post. Again, does not help. Use a wider post. It is counterintuitive to the process. So option A gives the correct answer. It's all about pressure. Question number 17 is invoked from memory. Which process is called what? You can pause the video. You can see for yourself. It's very easy, very straightforward. The answer is option D. I'm not going to get into the details because you already know this. We've done this chemistry as well. Question number 18. It's an interesting question in terms of the vocabulary it uses, and it is repeated in some questions as well elsewhere. A sealed container, sealed container means that there is no leakage. And when there is no leakage, it means that the mass is not changing. Not changing mass. Why are we interested in the mass not changing? Because we understand that inside a cylinder, when the gas molecules are colliding with the walls of container, the number of atoms matter. If the number of atoms are less in quantity, then the pressure will be low. So no leakage means no change in mass, means that the number of atoms are not going to change for at least this question. So everything is going to come down to their motion. You have to think about its movement, not about the number of particles at a certain given moment. So eventually, he says that it's left in the direct sunlight, it will gain thermal energy, it will gain energy from the radiation, infrared radiation. Eventually, the cylinder explodes, okay, very evidently. How is this explained in terms of behavior of the gas particles? Now, this is where the problem begins. He says that the particles get bigger. This is inherently wrong physics. You see, if this gas were, let's say, a nitrogen gas, which is N2, is it possible that if you provide it with thermal energy, the size of the nitrogen atom changes? No, it's not possible. So this is completely wrong physics. A and B were completely incorrect. The molecules are not going to change their shape or size or diameter. The particles gain kinetic energy, sounds good, and hit the cylinder harder and more often, sounds good enough. Particles lose, no. You see, in kinetic model of matter, we've understood that the temperature is directly responsible for the kinetic energy of particles. If you have a glass of water at 25 degrees centigrade, and if you have a glass of water at, let's say, 70 degrees centigrade, although they maintain the state of liquid, right? But I can predict, I can see that the molecules that are at 25 degrees centigrade will be moving at a lower speed, and the molecules at 70 degrees centigrade will be much more agitated. They will be much more violent in comparison to the ones at 25. So when you increase the temperature, the molecular speed increases, the kinetic energy increases. So temperature is linked with kinetic energy from the chapter of kinetic model of matter. Question number 19, again a repeated question. I've solved this many times over. I'm going to solve this again. I'm going to use the shortcut, right? So since we're dealing with changing parameters of gas, so it's going to be very straightforward as P1 V1 equals to P2 V2, right? So pressure initially is represented with letter P, and he says that initially it's at 20 centimeters. I'm going to use a shortcut, of course. So this is going to be 20 times into P equals to P2, which we don't know, into V2, which is the current position, which is 50. So when you find P2, you do get the right answer, which is 0.4 times P, but is it the right physics? No, it's not. This is not the right physics. The correct physics is that you're dealing with the length of the cylinder. In this formula, you're supposed to use volume. So how do we tackle this? You see, since this is a cylinder, then if you wanted to calculate the volume, you should have used the formula pi r squared h. Now, when you do that on both sides, if you multiply this with pi r squared, now you don't know the radius of the cylinder, right? But it's going to be the same on the other side as well. You will find pi r squared on the left-hand side as well. Now, this eventually gets cancelled out from both sides, and only h remains as 50 and 20. So some students generally memorize it this way, but that is wrong physics. If you just want to do the shortcut, it's fine. The examiner does not know what you did. But if you have to do this in the P2 question, then I would certainly recommend adding the pi r squared h to elevate your paper to at least a distinction level that you knew what you were doing. You didn't memorize the process. But okay, the length can be replaced as a volume. This is wrong. Okay, but anyways. Question number 20 is from conduction to metal radiation based on memory. He says that one of them is just left to cool down and one of them is constantly being provided with heat. And pot X contains water below its boiling point and pot Y contains water that is kept boiling, it's continuously boiling, by a hot plate underneath it, by induction stove. What happens with the kinetic energy? As discussed earlier, the X will lose kinetic energy, right? It's generally going to release its energy into the environment by radiation. Then we have pot Y that is constantly, let's say the boiling point is 70 degrees centigrade, for the sake of example, okay? And it is kept under the boiling condition. What's happening with the kinetic energy of the liquid in pot Y? You see, when the boiling point is reached, the temperature of the liquid stops increasing. But then the question arises, where does the extra energy go? That extra energy that you keep providing to the system is actually converting into steam, or converting water into steam, or is being utilized in converting the state of that liquid molecule from liquid into gas. Okay, so but the temperature does not change. That's why it is called a boiling point. It's a fixed point. You keep on providing energy, the boiling point or the temperature does not change, and hence the kinetic energy does not change, because kinetic energy simply makes this binary decision that is the temperature changing? If it's not changing, then the kinetic energy is not changing. Plain and simple, no questions asked. So this will be 20B. Then we have question number 21. It says solid metals are good thermal conductors. Okay, fine. How closely packed are these particles to the metal contains free electron, and do they contain that? So what is the packing of the metals? We are solid, so they're very close together. Very straightforward question. And do they have free electrons? Yes, they do. So 21 is B. That's why metals are good conductors, because they have free electrons. They can move and move energy from one point to another. Question number 22 is again asked from memory, which students generally forget, because this question is not very apparent, or you can say it's not repeated as much as the other ones. It says cotton wool is a good thermal conductor. Okay, fine. Contains threads that are tangled together. This is just extra information. He doesn't want anything to do. This has nothing to do with the question. Diagram shows the structure of the cotton wool. Okay, why is the cotton wool a good thermal conductor? Because there are spaces between them which are filled with air, and air is a good thermal insulator, right? So the thread is very thin, doesn't have to do anything. Even if it would have been a thicker thread, it wouldn't change the outcome. It has a large surface area, again, no issues with that. A surface area is linked with evaporation. Just trying to confuse you with that. It has a low density because of trapped air. No. It traps air and prevents convection. This is the closest option, the closest answer that we can get in terms of the true answer. And that is what happens when you're wearing sweaters, when you're wearing jackets, when you're wearing thicker clothes. What are you trying to do? You're trying to trap air between your skin and the cloth, but the cloth is helping you do it, so that the thermal energy produced by your own body does not escape into the environment. That's all that you're doing. Okay. Question number 23. Metal is heated. Okay. Thermal energy transfers to the bottom of the kettle and within the water. Now through the kettle, of course. Now through the kettle, if you're dealing with a solid object, it has to do with conduction, right? The metal base is a solid. This grid is a solid. And the grid is being heated by the radiation. The grid is then heating, or is in contact with the metal base. The metal base is then being heated up. So this is conduction. It would have been A or C. Okay. Within water, of course, there's going to be convection. Conduction takes place from solids, okay, or to stay in contact. But then you can argue that the water is in contact with the base of the solid as well. Yes, that's true. That the water molecules closer to the base, they will absorb energy by conduction, but they are going to transfer that energy to the next water molecule by convection. Okay, so he's asking me within water. If he had asked me how it is transferred to water, then of course that would have also been conduction. Okay, so this is 23C. 24, straightforward question, wavelength of a longitudinal wave. First, this is not a longitudinal wave. This is a longitudinal wave. It has to be from the center of one compression to the center of next compression. Most probable answer is option A. B has no meaning in a longitudinal wave. But what about if the wavelength had been asked for the transverse wave, which is on the right side, with option C and D? You see, C is still wrong, because this is only representing half a wavelength. If you wanted the full wavelength, then one trough and one crest and one trough should have been a part of the answer. Then it would still have been a confusion, okay? But since he's asking about longitudinal, then it's very straightforward. A is the answer. Question number 25, this concept is new in terms of O-level and IGCSE. He says a student is standing at point X, shown the view above. Okay, fine. The door is classroom closed. X hears the bell ringing. Okay, fine. The door is open. The sound is heard by the student from the bell is louder. From the bell is louder. That causes, okay, what causes the sound? Okay, fine. You see, how can the student hear the sound? Now, when this wavefront is produced by the sound wave, the sound is traveling like this. But we understand that sound or waves or even radiations, they bend when they encounter a corner. They bend around a corner or around a gap. So these wavefronts that are going to encounter the door are going to move somewhat like this. They're going to go like this. And as a result, when you complete those wavefronts, right, these wavefronts are going to reach the student standing at X. So some sound is going in the forward direction, that is as it is. The sound that encounters this edge is going to get converted, or as you can say, it's going to get bent inside the gap like this. And you will see the same question in terms of electromagnetic radiation, that for example, this is the radio transmitter, and this is a mountain, and this is a house, for example. This is a very repeated question as well. How is it possible that the person sitting in the house can see the TV station as well? The radiations or the radio waves are actually moving like this. How can the person see the channel as well? You see, when it encounters this edge, the wavefronts bend around the edge like this. And as a result, the person also receives the signal. So question number 25 is going to be a repeated question, and it's going to be 25, option A. Dispersion is when white light disperses into 7 colors. This is certainly not the case of that. Reflection is when it bounces from one point to another. If it had been reflection, then the sound is going to get reflected back. How is it going to get to the student? Refraction is a change of medium. You're still standing in air. This is air, and this is also air. There is no change in medium. When there's no change in medium, the refraction would not have been the answer. So even by elimination, this would have been option A. So question number 6, a repeated question. I think I've seen this question 3 to 4 times in the past papers. Now, how to solve this question? He says, where is the girl's image? We know by the plane mirror, the image is formed directly in front of the person, and it has to have the same distance. So the distance of the girl from the mirror has to be same from the mirror inside to the image of the object. Okay. And how will the boy see it? We can see the boy sees he says the boy sees the image of the girl. How will he be able to see this? So the image is formed at this location, and the boy will be able to look at this image by this method. Or you can say by this light ray is how the boy can observe the image of the girl. Okay. All right. 27, a very straightforward question. It says that the angle in water, and this is the normal, angle in water is 40 degrees. What's the angle of incidence in air? What is this angle of incidence? And the refractive index is 1.3. So the formula goes something like this, that the refractive index is equal to sine of I divided by sine of R, right? So we have this as 1.3 equals to sine of I divided by sine of 40. You take it over there and you take the sine inverse. Your I is going to come out as 56.6 which is D option 57. A shortcut of this question would be that sine of sine of rare medium is divided by dense medium is refractive index. So the dense medium is water and the rare medium is air. So the smaller angle generally will come in the numerator and the larger angle will come in the denominator. But of course, with this shortcut, you have to memorize, you have to keep in memory that the angle of the rare medium or the angle of incidence in rare will be greater than the angle of incidence in the dense medium. Question number 28, he tries to ask you whether you remember the condition of total interreflection or not. He says that a light is through the triangle glass block. Which angle is the critical angle as a angle of the light in the glass? You see, for the critical angle or total internal reflection to take place, the light should be moving from a dense medium, let's say glass, to a rare medium, let's say air. This is the first condition. So can it be from option A and B? It's not possible. A and B is not possible. But why? Because the light ray is in air and it's trying to go into dense. So it nullifies the first requirement of total internal reflection. So I can't even choose A and B. If I had to make a guess, it should have been between C and D. But anyways, let's move ahead. Now, at what point is the light trying to go from dense into rare? At what point is it going from dense to rare? Is C the angle of incidence or the critical angle? No. This boundary will decide whether I should choose the angle C or D. Is from this boundary light trying to go from dense into rare? If my answer is yes, that means this is where all the angles will be selected for critical angle, or at least all the other discussions in terms of total internal reflection. Now, and again, critical angle is the angle of incidence in the dense medium for which the angle of refraction becomes 90 in the rare medium. So option D is the right answer in terms of total internal reflection. Question number 29 is again a repeated question in terms of magnification. He's going to ask you that what's the magnification? So first, you're going to zoom in, of course, and you're going to count the number of boxes, and you will realize that this is approximately 1.5 centimeters, or at least 1.5 boxes. Okay. Then you will count the height of the image. So this is box number 1, box number 2, box number 3, and approximately box number 4, and then box number 5. So this is going to be 4.5 boxes. 4.5 centimeters, 4.5 boxes. The formula goes height of image divided by height of object. Okay. For magnification, so this is 4.5 divided by 1.5. When you solve this, you're going to get your answer as 3. So this is question number 9. 29 is going to be option B. Question number 30, again from electromagnetic spectrum, you have to memorize what spectrum is used for which application. Which application uses ultraviolet? Now, Bluetooth is from microwave. Even your Wi-Fi is from microwave. Prenatal scanning that is done for ultrasound is not even an electromagnetic wave, it's a sound wave. Sterilizing water, that looks like a good option because ultraviolet is used to kill bacteria. Thermal imaging, no, that's for infrared. This is for infrared, so C is the best answer. So moving on, question number 31, he says, okay, held in hand, which rod gains a lot electrostatic charge? So polythene rod, good. Steel magnet, no. Magnets don't have to do anything with static charging, okay? Plus, if you are dealing with steel or let's say an iron rod and you're holding with bare hands, whatever charge you're going to gain on that rod is going to get transferred through your hand into your body and then grounded into the ground. So it's highly unlikely that you will be able to store any static charge or any piece of metal if you're holding with your hands. If the person was wearing gloves and you're insulated, then we could have discussed it. So steel magnet and iron rod with a woolen duster is all right. Steel magnet is not all right. These are not possible. Charges won't stay on that rod for long. So polythene rod, yes. Topped with a woolen duster, yes. Polythene rod, why? Because whatever charge it gains, it will not be transferred because it's plastic. So plastics don't conduct electricity. So whatever charges you have exchanged will stay on both of these objects. So option B is the right answer. Question number 32, again, from memory, very straightforward question, nothing to worry about. He says, there are 4 arrangements, which ones repel each other? So north and north should repel, they are going to attract. This is repel, this is attract. So 2 and 3 should be the answer, which is going to be option C. So 32 is C. Number 33, it says graph shows current voltage across a resistor of constant. Now, this is where the hint lies. Constant resistance means that the temperature is constant. And if the temperature is constant, in some sense, which is again probably not a part of your course, but in some sense, the gradient of the graphs should also remain constant. But then again, if you think about it in terms of gradient, then option C, D, and A all present a problem. Okay, only B gets eliminated by this idea. But first, let's eliminate option B. It's not for an element that has a constant temperature at least. And we certainly don't have an element in which you keep on increasing the voltage and the current does not change. Okay, that's not possible. Although this is a condition, but that does come for a filament lamp, but after a very, very, very long time, after a very high voltage. And we don't have electrical components that have a linear negative coefficient behavior. This behavior is for an RTD, or you can say not an RTD, but a thermistor or an LDR, okay, in terms of their respective quantity. But this behavior is difficult to find. A straight nonlinear decreasing behavior. So a constant resistance means constant temperature, and most likely he's going to talk about an ohmic resistor that has a fixed value. So the closest option that we had to question number 33 was option A. Very straightforward. I've discussed the other options, but a student who has this basic knowledge of constant resistance and Ohm's law would have selected this answer, option A, straight away, no questions asked. What he has done, he's swapped the axis for you. This is voltage and this is current, generally when we discuss Ohm's law, but we don't need that over here. Okay, even if the axes were swapped, a straight line will remain a straight line. Okay, all right. Question number 34, this is a bit tricky and this is actually solved in your book, but we don't have a habit of reading books. So that's why you may not be able to solve this question, but let me solve it for you. You see, he says, what's the comparison between series and parallel currents? What's going to happen? What you could have done is solved a question for yourself by hypothetical values, and it would have made your life a little easier at least. So let's make that hypothetical question. So what if we had 2 resistors in series to each other? Let's say this is 5 ohms, and the battery is 10 volts. I can very well clearly see that when I apply V equals to IR, the voltage is 10, the resistance is 10, the current is going to be 1 ampere in series. But when I connect them in parallel, let's say, then the equivalent resistance becomes 2.5 ohms. How do I know this? By 1 over 5 plus 1 over 5 equals to 1 over R. When you solve this LCM, you'll get 2.5 ohms. Okay, and the battery voltage is 10 volts. So in this situation, the current, if I use V equals to IR, this is 10 volts of voltage. Current, I don't know, 2.5 ohms of resistance, and the current is going to come out as 4 amperes. So the current in parallel combination and the current in series combination, one is 1 ampere, the other is 4 ampere, and it is series divided by the parallel combination. So this is 1 divided by 4. It's going to get you 0.25 as the answer. You could have done this by variable method as well, but I believe that for an O-levels and IGC student, that's a bit difficult. It would have again gone by the same method. You would have let the voltage as V. This would have been R and R. This would have been R and R. This would have been 2R. This would have been R by 2, and so on and so forth. You can try the algebra method as well. But most likely I feel that in such questions, it's good to assume a circuit scenario and just make sure that you do that for the second circuit in the similar fashion as well. It makes your life a bit easier, okay, instead of the algebra. The 35, he says that we have a generator connected to a lamp, okay. The generator is rotated at constant rate, which makes the lamp flash twice every second. Now, this is important information because this is the standard. This is what we're going to compare the rest of the situation to. The coil is then rotated at half the rotation. If you move the generator slowly, one of the things that's going to happen is that the EMF produced by the generator will reduce because the magnetic flux cutting will reduce. So brightness will reduce because the voltage is reducing, the EMF is reducing. What about the number of flashes? You see, after one rotation, it was flashing twice. If you reduce the rotation by half, the flashing will also reduce by half. So into question number 35, the straightaway answer was option A. The brightness decreased because of the Faraday's law of electromagnetic induction. Less magnetic field current means reduced EMF. 36. Magnetic effect of an electric current. So do compasses use that? No, compasses are magnets themselves. Or fuse? No, it relies on the fact that the current will be too high and I will melt and protect the circuit. Loudspeakers, looks like it. Magnifying glass, not at all. So loudspeakers, yes, they use the magnetic effect of current. We have a permanent magnet at the center, right? We have a coil at the center, something like this, okay, which is connected to the supply. Let me make this in a better format. We have a coil like this. This is connected to your computer or your mobile phone, or you can say the source of sound, and the cone which produces the sound is connected to the coil. So yes, we change the current in the coil, which responds to this permanent magnet, let's say like this. And we know that when current passes through a coil or through a wire, it has its own magnetic field, right? So the magnetic effect of current is most likely used in the loudspeakers. Question number 37, he says we have a magnetic field, which means that this is the North Pole and this is the South Pole, okay? He says there is a beam of alpha, beta, and neutrons fired into the magnetic field at the same direction as the conventional current. Okay, fine. Which beams experience a force that is initially in the same direction as the force experienced by the current carrying wire? Okay, so how to solve this question? So for this question, we have to assume all two conditions at the same time. Okay, so you see, neutrons have no charge on them. So neutrons are not going to experience any force. So it should be between B and D. Now let's make a choice between B and D. So let's say that this wire in this direction, let's say that the alpha particles were introduced with positive charge and beta were introduced with a negative charge. Okay, you have to use the Fleming's left-hand rule to figure out the direction of the force on these charges. So first, the first finger would be pointing upwards. The second finger would be pointing towards the right side if I'm taking alpha as the reference. And if I take, let's say, the direction of the thumb to be similar, to be in this direction, then the thumb would be in the outwards direction, right? Okay. And if we look at particle of beta, then the beta would be experiencing a magnetic field in the inward direction. So beta is inwards and alpha is outwards. So the problem that you will face at this point is that he's not asking about the direction, he's asking you about the direction of the current carrying wire, that the beta or alpha or neutron, out of these three, which of the atoms or which of the particles will experience a force in the same direction as the wire would have experienced primarily. You see, in physics, whenever we talk about the current carrying wire, we're always talking about the conventional current. And the conventional current talks about the fact that positive charges are moving from the battery, completing the circuit and coming back to the battery, which of course we understand is the wrong idea now today, because we understand that the electrons are doing the job. But since conventional current deals with the movement of positive charges, I understand it's wrong, but that is how physics has been moving since then. So the positive charge relates most closest to the alpha particle. So alpha particle would have been the particle that resembles the conventional current, and hence my answer should be option B. Question number 37. Then we move towards 38. Again, a question from CRO. He says that a diagram is shown, the time scale is shown, which means that the time taken for this one complete wave is, if one box is 4 milliseconds, then this is 4, 4, 4, and 4. So this is one complete wave. It is taking 4 multiplied by 4, 16 milliseconds to cover, or 2. You can say the time period of this wave is 16 milliseconds. He says that the time base is now reduced to 2 milliseconds, which means that one box will represent 2 milliseconds. What will this wave look like? First and foremost thing, changing time base has no effect on the amplitude, right? So if the amplitude is 2 boxes, then the options should also have 2 boxes. Option B and D are rejected because they are changing the amplitude of the output. Time base has nothing to do with it. So now I have to make a choice between A and C, which one is going to be this way. If I haven't changed the source of the wave, that means it should still consume 16 milliseconds to complete one time frame. Now, if by 2 milliseconds I check this option A, you can see my one wave is being completed within 2 boxes. So 2 plus 2, a time frame of 4 milliseconds. Is that the time period? No, the time period is 16. This is representing a time period of 4, which means that option A is incorrect. By elimination, I reach option C. But let's solve option C as well. One of them represents 2. So 1, 2, 3, 4, 5, 6, 7, 8. Because the whole wave is taking 8 boxes now. So 8 multiplied by 2 is again 16 milliseconds, which means that I am still representing my original wave, which means that the option C is the correct answer. Question number 39 is tricky in terms of its words only, but let's be careful about this. He says the half-life is 2.5. Okay, thank you. He says the time between 0 to 7.5, it decreases by 70 micrograms, which means that he's not talking about the parent nucleus. He's talking about the daughter, that it has whatever amount it started with. Today, its amount is x minus 70. It's less. Okay, so let's start with this idea. So the parent was x. It first underwent the decay process and became x by 2. And the daughter today is x by 2 as well. Okay, then the parent disintegrated further, became x by 4. Where is this x by 4 going? It's going to the daughter. This is the parent and this is the daughter. Previously, the daughter was 0. Today, the daughter is going to be x by 2 plus x by 4. So this is going to become, let's say, 1 by 2 plus 1 by 4. So 0.5 plus 0.25. This becomes 3 by 4. So today, the daughter is 3x by 4. And if you total this amount, this becomes x. This also becomes x. This also becomes x. X by 4 plus 3x by 4. So the total amount of sample is still the same today. Again, the parent undergoes the decay again, and the parent becomes x by 8. Now, x by 8 of the parent, again, half of that is actually going to go to the daughter. So when you add this 1 by 8 again into this fraction, it becomes 7 by 8. So today, the daughter is 7 by 8 of the parent, and the parent is only 1 by 8. Okay. Now, how do I know that I have to go up to 3 half-lives? You see, one half-life is 2.5. He goes up to 7.5, which means that 1, 2, 3 half-lives, or you can say 7.5 divided by 2.5, I will get 3 as my answer, which means I have to go, or I have to check up to 3 half-lives, or my stopping criteria would be 3 half-lives. So that's why I'm stopping here. So it decreases by 70, which means that today 7 by 8 is actually my 70 micrograms, or the daughter, right? Because whatever parent has lost is actually converting to become daughter. So today 7 by 8 times percentage, or by percentage, is occupied by the daughter. So 7 multiplied by, so 70 multiplied by 8 divided by 7 will give you the answer as 80 micrograms. So the parent was 80. If you want to verify this again, you can just take it will take 10 to 15 seconds to verify this. So start with 80, make it half becomes 40, make it half becomes 20, make it half again, it becomes 10. And if you're dealing with parent and daughter at the same time, this is going to become 40, this will become 60, and this will become 70. All the while, the total stays 80. So this is 80, this is 80, and this is also 80. Okay, so this is the problem with this question. It's just a matter of words and picking out the letters. But it's a good thing he's actually testing this idea that you need to understand that we are only solving questions in classroom related to parents, but we have to solve the questions regarding to daughter as well. Question number 40 is from the space physics topic. Okay, he says that there is a redshift. Okay, fine. Okay. Redshift of the galaxy X is smaller. So it means that if I'm standing at Earth, this is galaxy X and this is galaxy Y. The redshift of X is less and redshift of Y is more. That means X is closer to me and Y is further away. Which galaxy is closer to X? Sorry, closer to the Earth. So closer to Earth is going to be X, because we've done this in Doppler effect and Hubble's law. That the galaxy that is closer to you will show the least amount of change in frequency or the least amount of change in wavelength from Doppler effect or in terms of Doppler effect. And the one galaxy that is very far away from you, it's moving at a faster speed and its change in frequency is also greater. So the faster recession, or you can say the galaxy moving faster or at a very high speed away from us, would be galaxy Y. The answer is going to be B. But it doesn't matter. It does not mean that galaxy X is not moving away. Galaxy X is also moving away from us. But since Y is further away, and the evidence is from the Doppler effect, it will be moving at a faster speed. So let's say it's moving away at 100 meters per second. This may be moving at 70 meters per second. And the Doppler effect or the change in redshift is, let's say, this is 50 nanometers. And this is, let's say, 70 nanometers. So greater change in frequency, greater speed, lesser change in frequency, lesser speed.